Afternoon, everyone, and welcome to this 45-minute webinar on equation-based modeling with COMSOL Multiphysics. I'm glad that you could join me today for this interesting topic. Now, please, if you have any questions, you may ask them using the Questions tab, and I'll try to get to them as soon as I can. Let's get started. During today's session, I'd first like to introduce you to our software, COMSOL Multiphysics. We'll then talk equation-based modeling, so what it is, why, and when you'd want to use it. In fact, one reason you may want to go equation-based is if you can't find a ready-made physics-based simulation environment for the situation you'd like to model. And that's why the demo I'll show you today is not the standard electromagnetics or structural mechanics type of problem. No, it'll have to be a bit more unusual than that. We're going to define and solve a set of equations describing the flight of a mosquito, as it's, well, hopefully, attracted towards a mosquito trap. Now, if you happen not to be a mosquito scientist, then don't worry. The principles and techniques we'll be discussing are quite general. And after the demo, we'll look at the interfaces we offer for setting up and solving your own equations. And then we'll conclude with answering any remaining questions. And as mentioned, if you have any questions during the presentation, please ask them at any time. COMSOL Multiphysics is a platform for modeling and simulation. So you set up your simulation, mixing and matching physics interfaces from the base package or one of our 35 add-on physics modules. You can connect your simulations with external software, for example, for CAD. And we use finite elements, but also various other numerical methods. And we'll do some particle tracing today. Material properties are available, or you can choose to enter them yourself. For many of our users, creating a model that you're happy with is just the first step, though. You can then use our application builder to turn it into an easy-to-use simulation app that anyone can run. And you can compile your apps into standalone executables that will run anywhere with COMSOL Compiler. Or you can host them with COMSOL Server, giving your colleagues and customers access to them through a web interface. And to store, administrate, and cooperate around your models and apps, we also offer the Model Manager. Let me get you an idea of how all of this fits together, because COMSOL is modular software. In many cases, and in particular if we're going to focus on custom equations, the platform product, COMSOL Multiphysics, is all that you'll need. It has the model builder, in which you create your model. It has the application builder, in which you turn your model into an app. And it has the model manager, so you can organize and collaborate on your models and apps. And for distributing apps, you can add COMSOL Compiler or COMSOL Server. On the modeling side, although COMSOL comes with a number of interfaces, you'll often want to add one or a few physics modules to enable more specialized modeling within some particular field of physics. For example, while you'll be able to do linear solid mechanics with core COMSOL Multiphysics, the structural mechanics module enables you to model large nonlinear deformations, as well as beams or shells, for instance. And there's a bunch of multi-purpose modules as well, such as the uncertainty quantification module, which lets you address how an uncertainty in the input in your model propagates to a distribution in the output results. And the interfaces for setting up your own equations are part of the core package. So for what we're going to do today, most of that's all you're going to need. I'd like to explain what we mean by equation-based modeling. So let me contrast it with physics-based modeling. Here's an example of a model set up with our built-in physics interfaces, featuring resistive heating. If you'd like to create this model, you first select Joule heating from a list of common multiphysics scenarios. That gets you the interfaces for electric currents and heat transfer, as well as an automatic coupling between the two, called electromagnetic heating. Next, you pick materials from a list, assigning copper to the bus bar and titanium to some connecting screws. You then specify the electric currents part of the problem by applying an electric potential condition with, for instance, 20 millivolts on one of the boundaries of your geometry and ground on the other two. Finally, the heat transfer part of the model, where you assign, for example, a natural convection condition with a specified heat transfer coefficient, will worry. So when you're implementing it with the Poisson's equation, so what you do is for the electric currents, you specify that you want to solve for a variable called uppercase V. And between us, that's the electric potential. But to the solver, it's just an arbitrary variable name. And you furthermore name the diffusion coefficient sigma, and you specify that it should have different values in different parts of the model, representing, of course, the electric conductivity of copper and titanium. Poisson's equation for the temperature T has a source term representing the resistive heating, and that's sigma times the norm of the potential gradient squared. And this, well, if not before, that's where the power of equation-based modeling becomes apparent. All you need to do is look up the expression in a physics book and type it in. Your two equations will then become appropriately coupled and solved together. Setting up the boundary conditions is an equally mathematical rather than physical exercise. As the Poisson's equation can represent a lot of different things, you won't find any condition called ground, but instead you'll have a general so-called Dirichlet condition, which lets you set a value of the solution variable, which in this case is 0. I'm going to scroll down in my questions. Okay, seems we're back. Thank you. So, two different ways of interacting with the software, but with the same results, the same solution. So why then would we want to go for one over the other? If you want to set up a Joule heating problem like the one I showed you, I definitely suggest that you use the built-in physics interfaces. And that's why we offer them after all, to not have you reinvent the wheel every time. And to be honest, if you're among the vast majority of our users, you'll find that we have a physics interface that suits your needs rather perfectly. Just take a brief look at the interfaces on the left-hand side of this slide. I've opened up only the heat transfer folder, but there's a similar amount of content in many of the other folders that you'll find in the interface too. Now, my colleague, he actually had a nice analogy here. So picking a physics interface is like going into a bakery and pointing at a cake, as opposed to finding a recipe and spending an evening baking the exact same thing yourself, or a week in my case. Anyway, moreover, in some cases, it can be more convenient to pick a physics interface even if we don't happen to offer exactly what you're looking for. Now, suppose you want to model the flow of money going in and out of a small business under some set of conditions. You start looking into it, and eventually you realize that the equations you've come up with are the exact same as those that we're using for heat transfer in pipes. Well, then rather than re-implementing those equations, why not just use heat transfer in pipes, the interface, and just reinterpret the heat flow as a cash flow? This is an arbitrary example, by the way. Not quite sure that translates well, but you get the point. Now, if the physics interfaces are convenient and easy to use, then why would we use the mathematics interfaces? Now, I haven't mentioned this yet, but the most common reason to use those is if you want to extend the functionality of the physics interfaces. You can, for example, have them constrain the problem in some really arbitrary way. Say you want the pressure on the surface of your model to equal a function of the total thermal energy in some other part of the geometry. You're free to decide. Or maybe you want to have the influx of some chemical in your reactor tank depend on the concentration somewhere further down the line. Control system, maybe a PID regulation or some fancier scheme, up to you. Or you may want to compute a damage integral. That means you need to dynamically find the places in your geometry that have been exposed to an unhealthy amount of radiation or heat. Or you want to optimize your input parameters or the geometry for maximum performance. The choice is yours, and that's the recurring theme there. So all this and more can be done with the various mathematics interfaces, but you can also use them on their own, without any physics, to set up and model your own custom equations. And if those equations don't closely resemble anything that we offer as a physics interface, then that's a good reason to use a mathematics interface. We'll be talking some more about that later on, but for now, let's have a look at how we can apply equation-based modeling to a situation that we don't have any built-in physics for. And for that, we're going to think mosquitoes. First thing we need to do is come up with a mathematical description for how the mosquitoes behave. Absent wind and anything attracting the mosquitoes, I posit that they will be flying around aimlessly. and this is what we could call a random flight or maybe a three-dimensional random walk. And the first iteration is on this slide. X naught of t equals the sum of small random steps. I'm not a mosquito expert, but I don't think this is incredibly far from the truth. Anyway, the random flight is a good start, but not a complete model. If you've ever studied mosquitoes, you'll have found that they're drawn to the observer. They sense your smell and also the carbon dioxide that you're breathing out, perhaps even your body heat if you're close. And to make it easy, I'll lump up all of those effects, everything that's appealing to a mosquito, into a so-called attractor concentration C sub A. We'll then add a velocity component proportional to the gradient of that concentration. And that's the second equation that you see here on this slide. Physically speaking, what this expression is saying is that on top of the random movements, the mosquitoes will attempt to fly in the direction of the increased attractor concentration. And the steeper the concentration increase, the greater the velocity. And that's of course a bit of an approximation. We should probably, for example, impose a limit to the flight speed that the mosquito can reach. But for a first rough model, it will work just fine. You can see in the illustration here what a typical flight pattern might look like in a situation where the concentration increasing in the direction of the arrow. We are going to need a geometry for our model. And this is going to be our little mosquito-ridden cabin in the woods. So let's say we bought a mosquito trap for indoor use and want to try it out in this model to see if it does its job before putting it to the test in real life. We'll be leaving the side window open to let in the mosquitoes and place the trap some distance away from the bed, as supposedly we've been instructed by the manufacturer. Mosquitoes that come in will eventually find their way to the trap or to us. And what I'd like to find out from this model is their likelihood of reaching either destination. Now, neglecting any wind inside the cabin, we should be able to model the local attractor concentration everywhere using a diffusion equation. For simplicity, let's absorb the constant k in front of the concentration gradient to make it an equation for a velocity potential. That is, the non-random part of the velocity of the mosquitoes is going to equal, not just be proportional to, the gradient of this velocity potential. The equation that we have here is one of the most basic PDEs there is, and it's called the Laplace equation. It's easy to deal with and solves quickly. Now, let's assume the trap has characteristics making it 60% more attractive than human skin, for instance. So I'm going to conveniently take that to mean that it's got a velocity potential 60% greater than I have. And I've basically invented some numbers we'll use. So let's say 0.5 meters squared per second on my skin and 60% greater, or 0.8 meters squared per second on the trap. Now, let's switch over to COMSOL to set up and solve this equation for the velocity potential. For this demonstration, I'm going to assume that you've seen COMSOL before in perhaps more elementary webinars, but still, let's walk through this step by step. So we're first going to choose the model wizard, since it just helps us take the first couple of steps. We can work with several space dimensions. And if we have a problem that allows for, let's say, exploiting symmetry or looking at it from a side view or whatever you want to call it, then it can be very efficient to use less than 3 dimensions. But in this case, we'll stick to 3. And then we get to select the physics interfaces that will be present, right? So this is where I could add an acoustics interface. Or maybe I'd like to add a heat transfer interface, or perhaps something from the semiconductor module, you name it. I'm not going to do any of this, and instead I'm going to find the mathematics interface here, which has various options. We will be using the classical PDEs, and in particular, the Laplace equation. I'll add it, and then I get to already make a few choices. I'm going to rename my dependent variable capital V, which is going to be our potential, velocity potential. Then my units will have to be meters squared per second, because we want the spatial gradient of this to be a velocity. And the source term we can leave for now. Next up is a study. Well, this particular equation doesn't have any time derivatives, so the stationary study is the obvious one to choose, and we will. Done. Okay, so what do we have here? Well, we have our model builder, this is where we'll build our model, of course, and each of these nodes are configured through the settings window, and of course, the graphics window over here, let's resize it, can be used to visualize everything we do. I see. Every now and then I'm reading up on the questions. Some people keep having audio problems. So as I said, my internet connection dropped briefly, fortunately earlier. But after that, as far as I can see, there was only a small amount of people who were having trouble. So I'm afraid it will have to be something on their end. I think my colleague will try to help them out while we proceed. Now, first thing I'm going to do is I'm going to import a geometry, the one that we've seen before. So my geometry, of course, can be created in COMSOL itself, or we can import it from, well, something that has been created in COMSOL previously, or something has been created with a CAD software package, for instance. So I'm going to hit import, browse, and I'm going to find my cabin MPH bin files. I'll double click it, I'll say import, and here we have our geometry. Now, if I enable the wireframe rendering here, we can see a little bit better what's going on. So we've already introduced the geometry, but now we have it in our software. Then I need to work on my Laplace equation. First of all, and this is something you need to do with physics interfaces in general, you'll want to apply it only where this variable, capital T, or the velocity potential is supposed to live, let's say. So I'm going to clear the selection, and I'm only going to select the interior of my cabin along with the interior of my window, because that's where I want velocities. That's where I want mosquitoes to be. Next up, this zero flux condition that's applied everywhere needs to be replaced. So to that end, I'm going to add Dirichlet boundary conditions, which really are just prescribed values of my dependent variable, capital V. I'll keep it at 0 for the window. So think of this as our ground to our potential. Then I'll keep on adding these. First of all, I'm going to add one to my trap here, which needed the value 0.8, if I remember correctly. So I'll select the box, and I'll draw that box around this thing here. And then we can select the trap. Even though it's fairly simple, it's still a bit tedious to select this multiple times. So I'm going to use this button over here to convert this selection into a named one that I can reuse later. I'll call it trap. I'll do that one more time, but this time around I'm going to identify the skin. So let's zoom in a little bit with my middle mouse button, and let's use box select. I'll select this guy over there. Looks like I selected a little bit too much, so let's deselect that. There we go. And then finally, let's include this foot here that's, well, unfortunately sticking out of the bed. Well, you know how it goes. So, especially in this case, it can be beneficial to create a selection so we don't have to redo that. And there we go. This is all we need, just a Laplace equation with a prescribed value of our potential at a couple of locations. I'm going to keep my mesh at the normal one, even though, of course, to make this more accurate, I would need to refine, but for now it's okay. And I'm simply going to compute this. Hopefully it shouldn't take long. I made a mistake. Look at that. How did that happen? So let's check. 0, I forgot to set the values. I'm talking too much, that's the problem. 0.8 for the trap, 0.5 for the skin. There we go. Compute again. Happy little accidents. There we go. So now we have a non-zero value. Doesn't seem to go all the way up to 0.8, but that's simply because these slices here that we have don't intersect with the trap. So let's see if we can make that a little bit better. Slice 1, set it to one plane, and I'll set it to interactive because then I can shift this thing around a little bit. I can actually set it so that it hits the trap, and now I see that it nicely goes from 0.8 to 0, like I would expect. Even better though would be if I could add a streamlines plot to this thing. And I'm going to use the derivatives or the gradient, let's say of V, my velocity potential. And I want my streamlines to start at my window. And then if I plot them, I nicely see some streamlines adding up at the skin and some of them ending up at the trap. Now, I'm not taking the random walk aspect into account at all yet, but still, this is already a crude, very first approximation. I guess technically I could count these streamlines, count the ones that end up at the skin and the ones that end up at the trap, and already have a bit of an idea of the effectiveness of the trap. But of course, we can do better. So for that, let's see how we proceed. Well, we've modeled the velocity potential distribution. And it's fairly easy then to use that in a particle tracing simulation, which follows individual mosquitoes as they fly across the room. Our particle tracing interface has a Brownian motion feature that you can use for the random flight. And then you can add the contribution from the velocity potential that we've defined here. Do this for enough mosquitoes, and counting the number of mosquitoes reaching the trap or the skin as you go, you'll get a measure of the effectiveness of the trap. And I will show you this model in a minute, but first let's consider an alternative implementation. Because with particle tracing, you're looking at discrete mosquitoes, maybe 100 or 1,000 of them. And the higher the number you're sending in, the smaller the statistical error. But how about completely eliminating that error? And for that, we're not going to picture not 1,000 mosquitoes, but rather a continuous cloud of mosquitoes, just too many to count. Which isn't a very happy thought, by the way, but if you prefer, you can think of it as an evolving probability density cloud. The local concentration then represents the chances that you'll find a mosquito in a certain position at a certain time. And those two descriptions are equivalent, provided you neglect any mutual interaction between the mosquitoes. The continuum equation that you'll end up with, and this is derived straight from the discrete equation that we've used so far, is the convection diffusion equation. It has a diffusion coefficient that you can get from the parameters of the random walk. And then there's the convective part with the gradient of the local velocity potential from the previous simulation. And in this continuum model, we'll send in a concentration pulse and we'll see how it eventually distributes between the trap and my skin. And the boundary flux will be available from the solution, and we'll add a global equation to integrate it over time. Now, if you give me a moment, I'm going to open another model. There we go. So to save us some time, I've opened the particle tracing model here. So it has the Laplace equation that we already added. We can view the geometry and the velocity potential. It's the exact same thing we just computed, but now just a little fancier plot. But we've also added particle tracing here. It's only defined in the same domains as the other one. Well, and what do we have? Well, we specify particle properties, a mosquito mass and a mosquito diameter, right? Which we define through parameters over here. Then we have an inlet, which simply says the distribution of mosquitoes that enters my domain. And well, this is a detail, an implementation detail, but there's a number of particles that we release, and then the density has to be proportional in this case to the y derivative of my velocity potential, which is the derivative in this case. So the higher the velocity in that sense, the higher the density. And we are going to stick to the velocity that follows from our velocity potential. Inside the domain, we have a drag force. So this is the convection part. These particles, the mosquitoes, are dragged along by this quote unquote flow or the velocity that we've defined. And we also have the Brownian motion. So this, well, you can compute from the parameters. I won't go into the details, but this takes care of the random walk. And then we have two outlets, one for my skin and the other for my trap. And to make that useful, because they have the freeze condition for them, we add an accumulator, counting whatever ends up at the skin and whatever ends up at the trap. So the sort of post-processing we can do from this is we can look at the trajectories for every time step. So this is at TS30, where we've colored one particular mosquito just to show you how it flies. And we'll see that at TS30, most of the mosquitoes are focused around the center of the room. We could pass through this through time. You could actually create an animation, but it will probably be hard to see over the webinar. Guess I can show the final time, which looks like this. So we see many mosquitoes at the trap, many at the skin also, and our particular mosquito that we followed ends up at the skin through some semi-random path as well. More interesting is to use those accumulator variables that we've defined for the skin and the trap, and we divide them by the number of mosquitoes coming in so that we get a percentual distribution of, let's say, how many mosquitoes end up where for the skin and the trap. The last thing we'll do is we're going to add that convection diffusion thing. Now, if I add physics, I could add it directly from mathematics, right? If I look here at classical PDEs, I have the convection diffusion equation or even a stabilized one. But what I can also do, just to show you something else, is I could add a transport of diluted species interface, which really represents the same equation. It simply has a specific interpretation to it. And we'll see how to use that. First thing we need to do is we need to set transport properties. We have a diffusion coefficient. Well, we'll take that from a parameter. I won't go over the details on how it's defined. Velocity field, again, has to depend on the gradient of that potential we computed earlier. And then we need a couple more boundary conditions. Namely, we need an inflow one. So we need to tell COMSOL what comes in over here. And our concentration, this is going to again have to be, let's say, a sudden pulse. So at one point we release a couple of mosquitoes and then we wait until those have reached their destination. And in the continuous sense, we can do that. Well, we could add a time-dependent expression here, or we could use a built-in function. It's already been added here. So this is a rectangle with a lower and upper limit and an amplitude. We can plot it. So after 0, for the first second, we get some plot with some pulse, with some smoothing, helping the solver. And this thing we're going to use in our inflow. So I'm simply typing rect1, which is the function. Argument is t, time, and I'm adding a unit to prevent any warnings from COMSOL, like this. And the other boundary condition I'll use is the open boundary condition. So I'll set it first on the skin, and then, I should, my bad, not forget to only add the transport interface to the interior as well, just like I did with the other two physics interfaces. And then we can specify an open boundary for the skin, and we can specify another one for the trap. And the advantage to this thing is, and that's why we can use this transport of diluted species interface instead of the mathematics one. I mean, we could use that one as well, but then we'd have to implement this condition ourselves. And what this thing does is it basically says, if our velocity is going outward, then we basically have a no flux condition. But if locally, for some reason, it becomes inward, so if there is a velocity away from the trap or the skin, then we just want 0 concentration. Conveniently implemented using the open boundary condition. So we're almost out of time, at least for the talking part. So I'm going to open the finalized part of this model. 1 second, open. All right, we'll continue. So this is once again the same model, now with the transport thing added. And notice we have global equations here. So what do they do? Well, this is really a post-processing feature. You can use it to define aspects of the model, but here it's used for post-processing. How does it work? Well, we have defined non-local couplings or integration operations under definitions. And these integrate over the window, the skin, and the trap. So what we want to do is, this is a spatial integration, but we also want to integrate through time. We want to find out how many mosquitoes basically end up at a certain destination. So what happens is this. For instance, the number of mosquitoes coming in, N, is defined such that this expression is 0. That's how you have to read this. And what this says is the derivative of the variable we're trying to define has to be equal to the spatial integration through our integration operator of the flux of concentration. So what that means is this does the spatial integration, while this here, specifying a value n by defining its time derivative, that takes care of the temporal integration. So how do we use this? Well, we can of course look at the convection diffusion results. Here again, we have it for 30 seconds, and we again see that the majority of the cloud is focused in the center like we saw before. But the most important thing would be to look at this plot again, which we've made for the particle tracing simulation, remember? So we've looked at those accumulators we added earlier. And now we're going to add another one where we make use of those integrated variables from our global equations. The number of mosquitoes ending up at the skin and the trap divided by those that came in. And if I plot that, we conveniently find that the results are very, very similar to the particle tracing simulations. Refine the mesh, increase the number of particles or the number of mosquitoes, and in the limit, these should be exactly the same. I think that's a very interesting experiment into working with equation-based modeling and implementing your equations in various ways. So, one more time, the results from the models. I have a question though. Could you please explain global equation once more? For example, where n int has been defined, of course. So, it takes some getting used to, but once you see it, it's basically easy. You have to look at these expressions here. We name our own variables, and then we define any expression that COMSOL forces to be 0, basically. So what's happening here is n in t is the time derivative. So this is a built-in expression. This means the time derivative of the expression we're defining. So we're prescribing an expression that we force to 0 that involves the time derivative of our variable. And we're forcing, due to this expression, this time derivative to be equal to the spatial integral of the flux of concentration. So again, this spatial integral here, this defines a boundary. So this defines where it is and says that it's going to integrate over that boundary. So by writing int op in of minus TDS dot anti-flux C, which is a built-in flux variable. So this expression here gives, well, that flux integrated over that boundary. And the whole thing equates that integral, or yeah, let's say the result of that integration, to the time derivative of our variable, meaning this will actually be, well, the temporal integration of the spatial integration of the concentration flux. So I hope that actually clarified it rather than confusing you even more. Please let me know if it's still not clear. All right, where were we? So we've talked about the results, right? Let's proceed. Because we've been using the Laplace equation interface and a convection diffusion based interface today. And there also are some more comprehensive interfaces available if you want to set up some more general partial differential equation. So for instance, we've got this coefficient form PDE, which lets you fill in values or expressions for a long range of first and second order temporal and spatial derivatives. And it tends to be the easiest one to use because the alternative is the so-called general form PDE interface, but that one's more convenient if you want to implement a conservation law, for instance. And no matter which of these interfaces you choose, you'll implement your own equation by matching its coefficients with those in the interface. Look at this heat conduction equation, for example. It's solving for the temperature, capital T, which will correspond to the generic solution variable U in the interface. You'll find a du dt term and a coefficient dA in front of it. Just set dA to rho times Cp, and you'll have re-implemented the time derivative term. Next, there's a diffusion coefficient C, which we'll set to K. And finally, on the right-hand side of the equation, the interface asks for a value of F, which is our capital Q. And we need to be sure to set all other coefficients to 0, and you will now have our heat conduction equation implemented manually. Now, for lots more, please visit COMSOL.com. We've got an excellent blog there with plenty of blogs on equation-based modeling, blog posts. There's also videos, user stories, and a wide variety of models and apps available for download. Since some time now, we also have the renewed Learning Center with several articles that can get you going on this topic and others. And if you'd like to try out this software or have any questions, please get in touch with us. So we have 5 minutes and a little more still available for some extra questions. So if there are any, please ask them. Thank you for your attention. Someone asked how to set up a physics builder for creating a new physics interface. Okay, that's also an interesting one. So we do have this physics builder tool if you really want to implement your own interface. I'm afraid I cannot cover that in these 5 remaining minutes. And to be frank, it's been a while since I've used it. So I wholeheartedly invite you to reach out to us through support if you'd like to know more about that, and we can have a look at it together. Scroll back up, see if I missed anything. Someone asked for an FET-based gas sensor. How can we define a variable for equivalent gate voltage for controlling drain current? Also rather specific questions. I wish I were able to answer that straight away, but this is also a very good one, I think, to ask us through support. Maybe include a model that you've already created, or some reference, some theory that you're basing yourself on, and yeah, we can try to help as well as we can. Can we get the weak formulation of the PDE that we model using COMSOL? I don't think so. Well, let's see. I'll move back to COMSOL momentarily. We're still showing this, yes. So as you might be aware, by opening the Show More Options menu there and enabling the equation view, we can actually see underlying equations, let's say underlying implementations for the equations that are present for built-in physics interfaces. For instance, here we have weak expressions that correspond to the transport of diluted species interface. If I'm not mistaken, those are not available currently for the, they're not available for the mathematics-based interfaces, unfortunately. You're welcome. Someone asked whether it's possible to model a self-rotating sphere using another sphere in a point contact to obtain the impact of the rotation on each other. Yeah, that sounds like a solid mechanics type of simulation, possibly with contact features. So you would require the structural mechanics module for this, and we have several examples within the. So if you go to File, Application Libraries, and then under Structural Mechanics, you could find Contact, and there are several examples here. Snap hook, for instance, is an interesting one. And perhaps for this particular one, you could look at transient rolling contact too. If you're not interested in the stresses, but more in the behavior, let's say at a higher level, then perhaps a multi-body dynamic simulation would work as well. What else do we have? In global equations, how did you find the name of the TDS flux C? I mean the phrase in the parentheses. That's a good question. Let me show you. So actually, when I'm doing post-processing, right? So let's say I add a plot group, 3D, and I look at the surface. Then if I go to transport a diluted species for species C, here's a fluxes group, and here I will actually find the names of those variables. Sometimes, alternatively, it can help to, if I'm in a text box, hold Control and press the space bar, which also gives me a menu that lets me find such expressions. That might be a bit of a shortcut. And if you really want to dig all the way to the bottom, we could again look at this equation view that we have here, because all these nodes, many of them will have some variables defined on them. Often the first node that you have in a section here, the equation view has the majority of variables. So I can also use any of these to define that expression. But in this case, I suppose I could most easily, most straightforwardly find it from post-processing. All right, so thank you very much for attending. I hope you've learned something new, or at least found some inspiration to continue with your own modeling. As always, reach out to us if you have any further questions, and we'd like to see you again.